All right, welcome back everybody to our next topic on bios and ecosystems, sort of looking at the big picture of everything together. And the first thing we should talk about in doing this is about the place you live, called Earth. And you probably already know this, but just in case you don't, the Earth is revolves around the sun, and it takes roughly 365 days, which gives you a full year, for the Earth to go around the sun. It's a little bit off. That's why we have leap year and things like that, where we have to, take a day here and there. But for the most part, it takes about 365 days for the Earth to revolve around the sun. And then the Earth also is spinning on its own axis, and it takes about 24 hours for the Earth to go around, and that's what gives us daytime and night time. Okay, so they both go counterclockwise, and they take 365 days, which gives us our seasons going around that way, and then daytime, which takes day and night, which takes 24 hours. The other thing is that the Earth, if we're to sort of draw a line, the Earth is not spinning on its axis straight up and down relative to the sun, but rather it's tilted. And it's tilted about 23.5 degrees. So there's a little tilt in there. So the Earth spins on its axis kind of like that. And that's kind of important because that will then relate to our season. So what happens is, because of the tilt of the Earth, the directness of the sun rays in the northern hemisphere, for example, when the Earth is here, you get more direct sunlight hitting the northern hemisphere than you do the southern hemisphere in what we call the summer solstice, and in the northern hemisphere. And then when the Earth has come around this way and it's on this side of the sun, in this picture, what happens is the rays hitting the Earth are more directly hitting the southern hemisphere more, so you got a more direct input there. Then as you move this way, we'll talk about this, but you get less direct rays hitting the Earth here, and that gives us the winter solstice again in the northern hemisphere, and then it becomes summer in the southern hemisphere. So we'll talk about that. If you took a flashlight and you took a ball, and you say you took a basketball and shined a flashlight on it, what you would find is that as the light comes to the basketball, the equator, or the center of it, gets the majority of light, and then the light tends to sort of be reduced as you move this way. Okay, so what ends up happening is, because of the Earth being round, essentially, you get most of the direct sunlight hitting at the equator. And since the Earth is tilted at 23.5 degrees as it rotates, what you find is that at the equator, and roughly between here and here, you get most of the direct sunlight, and then the sun gets reduced as you move north and south for the most part. We'll revisit that again in a second. So if we zoom in and look at that up close, here's the sun right here, for example, shining down. Here's the equator. So it's just the Earth is turned this way. And I love this picture because I always point out, okay, so as the Earth heats up right here, what happens to warm air? And you should know warm air rises. So as warm air rises and takes moisture with it, what happens as the air gets higher up in the air, say 20, 30,000 feet? Most of you know, hopefully, that what happens as you get up here, it gets colder. But I always like to point out, hey, here's the sun. How is it getting colder as you move towards the sun? So I'll give you a little hint here why I like this. This is a very inaccurate picture. It makes it look like here's the cloud, and if you go just a little bit further, here's the sun. But in reality, this is 90 million more miles away or so, or even further than that. And so the sun really is not in this picture. So you're not really that much closer to the sun. So what happens here is it's a pressure thing. So there's molecules attracted to the Earth that creates high pressure here and low pressure up here. And when you have low pressure, what ends up happening is it gets cooler. And as it gets colder, what happens is hydrogen bonds form and water starts to connect to itself and forms rain. And so the water tends to drop down. The air, which is now cool, would drop back down, but it's being pushed by more warm rising air always. So what ends up happening is that air gets displaced and pushed along like that. And these are what we call Hadley cells. So Hadley cells are these basic airflow patterns that we see. And so what happens at the equator and between 0 and 23.5 degrees north and south, you have warm rising air which releases its water, which drops down, and you get a lot of rainfall right in here for the most part. And then that air, as it gets displaced and comes down here at 30 degrees, starts to re-warm. And so what you get here is dry descending air, which is one of the places you get deserts. So one of the things we'll talk about is that you tend to have deserts at 30 degrees north and south of the equator, but you tend to have tropical forests in this range between 0 and 23.5 degrees. Okay. I should also point out, though, that in addition to the Hadley cells and the wind flow, what you also find is that there are local effects that affect weather patterns. And so what happens is, in this case here, just to show you, this is called what we call a rain shadow desert. And this is the kind of deserts we have in the United States. So what happens here is as you're by the Pacific Ocean, for example, or any large body of water like this, the cool air from the ocean comes over like this. But as it goes up a mountain, what ends up happening is as you go up, same kind of thing happens. The pressure drops. And so as the pressure drops, it gets cooler. So the rain tends to fall here. So this is called the windward side of the mountain. And I see that I've cut off my word here, so I'll write that there. That's the leeward side of the other mountain, on the other side of the mountain. So as you go, say, over the Cascade Mountains here, it's cool here and you get a lot of rainfall. But as you go over this way, and it's still cold, the rain is pretty much dropped on this side because it's so cold, it's condensed and the rain is dropped. As you go down this, it tends to be very hot and dry. And so down here you get dry weather and tends to be very warm, and that's on the leeward side of a mountain. So a big mountain range like that is another place you can get desert. So there's not only the Hadley cells and the basic wind flow, but there's sort of the local geology also that can affect that. So one of the things I want to make sure you know is this map, which shows you the basic position of the biomes on planet Earth. And there's some common things you can notice here. For example, this is the Tropic of Cancer at 23.5 degrees roughly north of the equator, and the Tropic of Capricorn, south of the equator at 23.5. So what you notice in here, this dotted line here and here, that this is where you tend to get your tropical forests. So you can see tropical forest there, right there, all through there, all through northern Australia right there. All that's tend to be where you get tropical forests. And then at 30 degrees, for example, as I was just mentioning, 30 degrees north and south of the equator, you notice that you get deserts. So in this case, deserts are shown in yellow. So there's a little bit there. There's a little bit there. There's some there. North Africa, for example, a lot of desert regions there. Australia, right there. So you can see, because of the wind flow patterns, you tend to get these large regions, these biomes that we'll talk about in these areas, okay? We'll go through some of these more in a second. I should also point out here, though, once again, like local effects. So tundra, for example. Tundra up here, you notice this tundra is this very cold environment that often has land that doesn't unfreeze. It stays frozen year-round. You can get tundra, you'll notice, right here on the equator. Right on the equator, because it's so high up. So there's local effects where you get local effects like a high mountain range that even though you're on the equator, there are places where you can still have tundra. We call that alpine tundra in that case there. Okay, so go through a couple of the biomes here first of all, and just sort of give you a little introduction to them. Tropical forests, a bunch of different kinds of tropical forests. For the most part, they get large amounts of rain, although there are what we call dry forests. And again, located between 0 and 23.5 degrees north and south of the equator. Very rich species area, lots of species. About half of all the species in the world that we've identified have been from rainforests. There's lots of small populations of things, even species that only contain maybe, a few handful of individuals. And sadly, we're destroying that at a remarkable rate. About half of that is already gone for deforestation. They use it for wood and also for farming. And the big concern, not only environmentally, of taking this out and trying to just save the beauty of the nature, save the nature and the natural habitat, you often have to, unfortunately, try to show people how it relates to them directly. So rather than just pointing out, hey, we should save nature just because we should, some people need to know, well, how's it going to benefit me directly? Well, one of the things, for example, that you can point out to people is a lot of pharmaceuticals, a lot of pharmaceutical drugs that are prescribed to you have products that come, active ingredients from rainforest plants and animals. And we're discovering new drugs and medications all the time because what happens is, as you have this rich diversity, one of the things you get with rich diversity is you get a lot of genetic diversity. And when you have a lot of genetic diversity, those different genes can produce different molecules. And as you get a variety of molecules, those can be altered or used chemically, either directly or slightly altered using some biochemistry or organic chemistry. And you can make new drugs that way that could potentially treat cancer. For example, we have many drugs used to treat diabetes and cancer and things like that that come from rainforest found, tropical forest found plants and animals and things of that sort. The next group are the deserts. Those are located, again, 30 degrees north and south of the equator or on the leeward side of mountains. Also, you find them very far inland. You'll notice that in North America here, where we're at, we have deserts, but our deserts are actually, we have LA at about 32 or 34 degrees. So 30 degrees is actually down here through Mexico, probably right about there-ish or so. Not the second line, but this line right about there's around 30 degrees or so. I could be slightly off, but that's pretty close. But our deserts are not in North American California and Nevada, not at 30 degrees north and south of the equator. Instead, they're on the leeward side of a mountain. The way we define deserts typically is by rainfall. So deserts are places that get less than 10 inches of rainfall per year. And so you find cactus and things like that, species adapted to surviving very dry conditions. I should point out that we get used to the idea that, hey, deserts are hot. Deserts are hot because our deserts tend to be hot. But there are cold deserts as well. So there are deserts that are hot in the summer and cold in the winter, but there are deserts that are cold year-round because of being on a high altitude, but they simply just get very little rainfall. So don't be fooled by the fact that deserts are hot in the summer, for example, because not all deserts are hot in the summer. Some of them can be cold as well. If you look, here's a map of a place you might recognize you live. Here's West Covina. Not sure I can find Walnut in there. It might be right about there. Maybe not. Pretty close. Here's Pomona. So we're in here somewhere. Pretty close. But you'll notice, I'm going to point out here, here's the LA Orange County area right in here, Long Beach and so forth. Here's the Pacific Ocean. But you'll notice here we have the Angeles National Forest, San Gabriel Mountains, Santa Ana Mountains here. So we have this large mountain range right here. So you get this onshore wind, this wind bringing with it the cool air and water of the ocean. But as you go up the mountain, it tends to drop. The rain tends to drop. So where most of us live, depending on, I guess, where you live in all this, probably 95% of us in the class live, somewhere in this area here. But as you go over these mountains, it tends to get, say, up in Victorville and Barstow, the rain is all dropped. So it tends to be more of a desert as you go up the Cajon Pass and places like that. As you go up Interstate 15, or if you go far enough down I-10, you go over the mountain ranges and the rain has all dropped. Then this stays fairly cool and moist. So this is not technically a desert, although we have years and we've had more more of them, more and more lately, unfortunately, where we get less than 10 inches of rainfall per year. Historically, this region has gotten more than 10 inches of rainfall per year, and so therefore it is not considered a desert for the most part. What we have in our local biomes we have as our local biomes is what we'll either call chaparral or coastal sage scrub. I'll kind of mention the difference between the two here really quick, but these are located in coastal areas, which is where we're at, roughly 30 and 40 degrees north and south of the equator. So just above that desert line and all the way up to about 40 degrees north and south of the equator. Very fire adapted area. In fact, as I'm doing this video today, there's a couple fires burning, and some of my colleagues have had to evacuate their houses in the San Gabriel Mountain area right now. I'm not even sure exactly the extent of those fires of now, but we have fires quite often there in that hillside, mainly in the hillside. And so what happens is in most textbooks, you'll see this term chaparral. So chaparral is very common in Southern California, primarily though in the mountains. So what you'll find is in the textbook, they often talk about chaparral located in these coastal areas, but sort of as you go up the mountains a little bit where it's drier and tends to be a little more fire adapted. But as you come down the mountain to where most of us live, if you live sort of, below the mountain range there, at the base of the mountains down, that tends to be more what we call coastal sage scrub. So slightly different plants, not as fire adapted, pretty similar weather though, meaning we tend to have, in both chaparral and coastal sage scrub, you tend to have mild winters. That's how we describe it. Mild winters and warm summers. Now, today happens to be, a spring day where it's, 92 degrees at the beach even, and 100 degrees inland. Unfortunately, we'll have to rewrite all these textbook. But warm summers, in the city of Walnut, for example, I used to live in Walnut, and we would have the number of days over 100 degrees. You would maybe have 20 or 30 days over 100 degrees. Maybe it's more than that now. Maybe it's 40. Maybe it's going to increase. But where I did my research out in Palm Desert, which is a true desert, the number of days over 100 degrees is like, there's probably 150 days. Probably half the days were above 100 degrees. So we tend to describe where we live as warm summers. And that's mainly because of the number of days you have over 100 degrees as the deciding factor. Next is the taiga. This is the largest terrestrial biome. I should add terrestrial. Some books use the word biome to talk about just land, but other books, biomes are just large areas. So if you include the ocean is the largest biome really, but the largest terrestrial biome is this community called the taiga, this biome called the taiga, or the coniferous forest, located between 30 and 60 degrees north and south of the equator, mainly north. That's like northern Canada, the very northern part of the United States, most of Canada up in there, most of Europe, northern Europe and Russia and China up in there. That is all what we call taiga. Very few species of trees. The species diversity is low, although there's many individuals. So what you find is things like pine and spruce and fir. So you'll have a lot of trees, but not a lot of diversity, meaning, you have these three types repeated over and over again, and then a few other things here and there. This also where some animals that you might be familiar with, like moose and wolverines and elk, are found, mainly animals that can survive cold winters for the most part. And if you move north of the taiga, and also up in some high mountain ranges like right here, even on the equator as I mentioned and elsewhere. But north up here, north of the taiga, is the tundra. And in the tundra, they tend to have very short summers and very long cold winters, and often defined by this ground they call permafrost. So permafrost is ground. It's so cold there it tends to stay frozen year round. This is a picture, beautiful picture here of the tundra, like in the summertime maybe, or late spring. So normally this is like as good as it gets. So you notice there's no trees really for the most part. It tends to be very, very windy, so you don't have trees. Most of the vegetation is small and mat-like, and this is a tough environment to live in. Arctic foxes and polar bears live in regions like this, where you have to be able to survive really, really cold weather. Grizzly bears often will move between the tundra and the taiga, depending on the season, but in the winter it's quite a tough place. And as I mentioned, most of what we talk about is Arctic tundra, being way up here north, but you can have alpine tundra also. Anywhere in the world, anywhere you're high up on a mountain would give you alpine tundra as well. Next one is deciduous forests. These are found in a variety of places, like on the northeast coast of the United States, also parts of Europe. You notice over there in Australia. These were locations where you have trees like maple trees. Deciduous forests are mainly composed of trees that are deciduous. A deciduous tree is one that drops its leaves or loses its leaves in the fall, and a lot of the deciduous forests have been damaged by acid rain, very susceptible to acid rain. You get acid rain when you have pollution, so as you increase your pollution rate, it doesn't even have to be local, it can go up into the air and move around, but sulfur and things like that, nitrous oxide, those combine with water and form nitric acid and sulfuric acid and carbonic acid and create what we call acid rain. The next thing we'll do is we'll move into talking about aquatic ecosystems such as the oceans. Very, very big ecosystem. Largest of the biomes or ecosystem is the ocean. 71% of the earth is covered by ocean. The Pacific Ocean is the largest and deepest that we know of right now. The Mariana Trench, for example, in the Pacific Ocean, I think it's around a little over 30,000 feet deep. Very, very deep, and we're discovering new species in here all the time. High diversity in these intertidal zones. If you take Bio 2 or you ever get a chance, one of the cool things you can do in Southern California is you can go down, if you're nice and very careful with the species, is go down to the intertidal zone, because you can see all kinds of living creatures down here if you go down at low tide that live in these tide pools, and we often take field trips down there. So very high diversity there. Less diversity as you move out here, but this is a very huge portion of the earth that is still being discovered even today. Next thing we're talking about are freshwater ecosystems. Freshwater is simply water that is not salty. So water that does not have things like sodium and chloride in it like you would have in the ocean, or potassium chloride, things of that sort. And only 3% of the earth is freshwater. So these are streams, rivers, lakes, ponds, and things like that. And only 1% of that is drinkable. So one of the big scares right now that people should be worried about, and you start to, all my years now at Mount SAC, I'm in my 15th year now at Mount SAC, and I've seen this become more and more of a topic of conversation. But water is going to be the new big thing, like oil was in the 70s and 80s and still is now. But what happens if you run out of drinkable water? What are you going to do then? So we're having a big, serious issue right now with drought and getting fresh water and drinkable water. If you get a chance, and if you do this, I don't know if you're going to do this for extra credit, but one video that I find very interesting and very educational is the video documentary called Tapped. And I think it's very interesting. It's changed my views tremendously on water and that kind of thing. So you might want to check that out in all your free spare time. And then the last thing we'll mention is this idea of an estuary. So an estuary is where you have fresh water that sort of comes into contact with salt water. So if you have a stream or a river and that dumps into the ocean, that creates what's called an estuary. So you have fresh water that meets an ocean. These are areas usually that are very impacted by humans. So this is probably the most endangered ecosystem of all the ecosystems. There is some debate. Some people say, well, the tropical forests or coral reefs are more endangered or more destroyed, and that could be, but less than 1% of ecosystems are in even good condition. Less than 1% of estuaries are even in good condition at this point. Mainly because this is prime habitat for humans. The weather is usually good. There's access to taking freshwater boats and fishing and things like that into the ocean. And if you live, for example, along the coast here, our estuaries in the United States, for example, we'll build a road, we'll build a freeway or a bridge right over that and fill that in or that kind of thing. And that creates a lot of damage to these ecosystems.